Alright, so 4.1's lesson was on transforming relationships. The content and language objective was I will learn how to transform functions to make them more linear. Now, the warm-up for that day was what kind of relationship would you expect from a country's gross domestic product, GDP, per person, and their life expectancy. Now, I did give you guys some time to talk about that. This is a video, I'm not going to do that here. What we determined was the gross domestic product was going to be the explanatory variable, and their life expectancy would be a response to that. So some people asked, well, why is that true? Well, think about this. When a third world country suddenly starts getting medicine and, people start making more money, they start getting more technology or more advanced, life expectancy tends to improve with that. Countries that don't have, as good medicine or, that kind of stuff, they don't live as long. Now, example 4.1 talks about mammals. So, on this scatter plot, there's actually 96 different mammals that are charted here. The explanatory variable here is the body weight in kilograms, and the response variable here is the brain weight in grams. So, they're trying to see if there's a relationship here, and if we can actually use this information to predict, other information. And I started off with the question, what can you tell me about this scatter plot? So, people told me there's 4 obvious outliers. So, the elephant, the hippo, human, and dolphin. So obviously elephants are much bigger creatures, so they have much bigger brains. Hippos, they're bigger, but they're not very bright, so they have smaller brains. And then humans tend to have pretty big brains because they're smarter. And then, so I asked about, is this linear? Most people said no. The information here is kind of curved. You can see a slight curve. And then we have 4 really big outliers. Now, if we take out the hippo and the elephant, my question then became, is this more linear? Or is it linear at all? The answer to that was, well, yeah, maybe a little bit more linear, but I wouldn't say that it was linear. It's super all over the place, and, it curves right here. Now, what this chapter attempts to do is to make things that are not linear more linear, so we can actually use that information to make predictions. That's the end game. So on this next slide, we have log applied to the body weight and the brain weight, and this includes the hippo and the elephant. This is all of the data. So as you can see, this is way more linear. It actually forms pretty nicely around this least squares regression line, and this is something we could actually use to potentially predict an outcome. So this is just basically saying that in words. Applying a function such as the logarithm or square root to a quantitative transforming variable is called transforming or re-expressing the data. And again, we want to make these changes so that we can actually use the least squares regression line. Now, a linear transformation, ironically, cannot straighten a curved relationship between 2 variables. So actually, things like log, which don't tend to be linear, when applied to something that isn't linear, makes it linear. Again, super ironic. So, example of a linear transformation would be units. So, a more specific example would be changing units from, let's say, centimeters to inches. Just because you redefine the units doesn't mean you're actually transforming, the way that it's going to be formed onto the graph. Just because you change the units, it'll typically look exactly the same thing. It's not going to change the distribution in any way. You can also think of it as like, let's say you had a data set and you added 2 to everything. It just shifts everything 2. Now, on this slide, we talk about monotonic functions. Now, I asked a few questions about this as, what do you guys think this means? And ultimately we decided, or we talked about, f of t is like your output, y, your response variable. T is like x. Now, this says that it increases in one direction, but does not specify what direction it is. Now, these 2 down here do. Monotonic increasing, this implies that if a is greater than b, so, a being further to right because it's greater, then f of a, your output, will be greater than f of b. So that means this should be higher than this one. So remember that when we're going this direction, the further right you go, the higher the number is. When you're going vertically, the higher up you go, the bigger the number is. And this is the opposite. If still a is going to be greater than b, but this time we're going to say that f of a is actually smaller than b. So here f of a is graphed lower than f of b, because this is going to be decreasing. It's going to go in this direction. And then here are some actual examples. Which of these transformations are monotonic increasing, monotonic decreasing, or not monotonic? And it asks for you guys to give an equation for each transformation. So the first one asks you to transform height into inches, or height in inches, sorry, to height in feet. And the second one asks you to transform height in yards to height in inches. Now, if you are going to write an actual function, you have to define things. So I said let x represent height in inches and y height in feet. And I told you guys you didn't necessarily have to write this down, but hey, if you want to write it down now, I'm not going to stop you. And the question is, how many feet in 1 inch? So there are 12 inches in 1 foot, but if you're going to transform from inches to feet, what you're actually going to do is you're going to be using a fraction. So if I want to go from inches to feet, I have to convert it by actually multiplying by the fraction 1 over 12. So this is actually monotonic decreasing. Whenever you multiply by a fraction, you're actually decreasing numbers, so that makes sense. If you're multiplying by a whole number, that would actually be increasing, which is actually the next example. So transforming height in yards to inches, again, let's define the variables. So let x represent height in yards and let y represent height in inches. We know that 1 yard is 36 inches, so if we're going to convert this, we have to multiply by 36 inches, and it's actually increasing right here. But again, these are linear transformations. These will not make your curved scatter plot more linear. These are just examples of monotonic increasing and decreasing. And then here are the actual formulas. So I provided you guys with the guided notes, and I did not have this information on there because I wanted you guys to write them down. This one's fairly obvious. Now this is increasing, so b, the slope, is going to be greater than 0. For decreasing, we're going to have that lower. And then over here for square, we have t squared, log, we have log t. And then over here we have, for the decreasing ones, we have 1 over the square root of t. Or, t to the power of negative 1/2. These are the same thing. And these are also the same thing. So reciprocal is 1 over t, or t to the negative 1 power. Now here are some facts. Eventually we're going to do a problem with this in class. If the variable to be transformed takes values that are 0 or negative, first apply a linear transformation to make all values positive. Often we just add a constant to all observations. This will make a lot more sense when we actually do an example. And then right here it says, then choose a power or logarithmic transformation that simplifies the data, for example, one that approximately straightens the scatter plot. We've already done this a couple times. We've done a couple with log at this point. But hey, if you're watching this, you're probably absent, so you have no idea about that. Alright, power functions. T to the power p for positive powers p are monotonic increasing for values of t that are greater than 0. So what that says is if t is greater than 0, and you have it to some power, for the most part it'll stay monotonic increasing. They also preserve the order of the observations, and this is also true of logarithm. And then basically the opposite can be said for monotonic decreasing. The only issue with these is they reverse the order of the observations, which you don't always like. It's not necessarily a good thing. Alright, so powers of transformation, t to the power p for powers p greater than 1 are concave up. Now, if you want to see this in an actual calculator, plug in x and then put it to some power that's greater than 1. So it says right here, greater than 1. So you can start with 2, you can go 3, 4, 5. Any of those should look like this, where it's concave up. Now, the opposite can be said for concave down. So power is less than 1. So power less than 1 can also be fractions, like, technically the square root is power of 1/2. So technically you can use that as well, and they'll look like this. They're concave down. Alright, and then this is an example I also wanted you guys to try out. This is to try to build the ladder of powers. So on the same graph, plot x, and then to the p power, these are the different powers. So this might take a little while, but let's go ahead and do that here. Now I only care about the first quadrant when working with these kind of things. So I'm going to go X, and I'm going to move my calculator this way first. So I want to do all of these, so I'm going to go to the fourth power first, and then I'm going to go to, I'm going to have X squared, and just X by itself, and then I want the square root of X, and then X to the power of 0 is just 1, so you can plug in X to the power of 0, or you can just put in 1. That should form a straight line. And then finally, we also want to have X to the negative 1 power. Now, I don't particularly care about what this looks like everywhere. Like I said, I only care about the first quadrant. Real quick, I'm going to go over here and turn off my stats plots because I don't want those interfering. And then I'm going to change my window. I want this to be 0 to, let's just say 10. Keep it simple, keep it small. And I'm hoping this looks like what I want it to look like. Make sure I don't get zoom. So that's one of the lines. That's another one. That's my third one. My fourth one. The fifth one should be a straight line because that's 0. Or the power of 0. So this is just to give you a visual of what the different powers can potentially look like. And yeah, I want you guys to sketch that. Alright, now 4.2 actually talks about, this is a scatter plot. It's very curved, and actually it talks about the warm-up. So I'm not going to repeat that content. You guys can read it yourself. So this is very curved, but it has, a decent correlation. This is untouched. This is the raw data. Now the second one is we have the square root of just the gross domestic product. It did straighten it out a little bit, but overall it's still pretty curved, and then it actually strengthened the correlation as well. And then if we apply log to just the gross domestic product, it makes it even more linear. There's still a slight curvature, but there's a really strong correlation here. And then this last one, they take basically a reciprocal and a square root. Yeah, this is not going to be super useful though, because this data is going down now. Yeah, it's a little more linear and definitely has stronger correlation, but ultimately, if we were going to apply one of these, I would opt for this one right here. Alright, so linear growth and exponential growth. Linear growth increases by a fixed amount in each equal time period. So that's like an arithmetic sequence. You're just adding 2 every single time. 2 is your fixed amount, just keep adding that. Now exponential growth is increased by a fixed percentage of the previous total. So this one has to do more with actually multiplying, and we'll see an example of this very soon. Alright, so what do you guys think when you hear of exponential growth? I think bacteria, I think investing, and I think my retirement accounts. Compound interest, guys. Let's see. Skip over that. I'm going to go ahead and